So good morning. Hopefully everyone can see and hear okay. I'm Dr. Amanda Glaze, and I'm really excited to be here with you today for the National Biodiversity Teach-In. I think it is absolutely fantastic what's going on with this and couldn't be happier to be here. So as you can see from behind me, I'm not exactly in the typical scientist's office. Right now I am sitting in my cabin porch in the Appalachian foothills in North Alabama because I'm on a little bit of a biodiversity journey of my own. And so before I talk to you about what I do and how I got into this, I was just going to show you very quickly what really inspired me to become a scientist. And so we can come back to this and talk about it in just a moment. But this is the town where I grew up. And when we talk about biodiversity, I always think about home because home for me is North Alabama. It is one of the most biodiverse states in the country and has some pretty incredible things to offer. So I'm going to actually try to show you this video very quickly of where I'm currently doing my research. I'm based out of Savannah, Georgia, so this is about 8 hours away from home where I live now. But it's pretty amazing, and I hope you'll enjoy it. So it's a pretty incredible way to start your morning to get to look out and see that out your back door. This is something that has inspired me. Being able to really see firsthand as a scientist just how incredible the diversity of life really is, and be able to take time to study not only that biodiversity, but to look at how we got to biodiversity and to also talk to people about their stories as they relate to science. So a little bit about me. I am an evolutionary biologist by training, but I also train science teachers how to teach science. My research has spanned a lot of different topics. So I started out doing applied molecular biology, which is looking at the detailed genetic codes of things. But I expanded into more outdoor biology. So as you can see from my video, I spend a whole lot of time outside, and I spend a lot of my time talking to people about their thoughts about science. And so with me, my goal is for every person that I talk to, for everyone I come in contact with, to come away from our conversations with a little bit more of an appreciation for science, whether it's the formal science that you see on TV or science fiction in movies, or just the things that you see in your backyard. So I always get asked, how did I become a scientist? I actually didn't start out on this path, but I think I've always been a naturalist. And I really hope that in all of you, you can find a little bit of a naturalist in yourself as well. So what is a scientist really? Honestly, it's anybody that has questions about the world around them. That's all that it takes to be a scientist. It doesn't necessarily mean that you have a degree in science. It just means that you want to know more. You ask why. You ask a lot of questions and are never really satisfied with the answers. So I grew up in a very small community in North Alabama and spent most of my time outside because honestly there wasn't a lot much more to do there than spend your time outside, going out in the woods, playing in the water. As you could see from the video that I showed you, there's a lot of really neat places that you can just go and explore and get lost. And so I went to school actually planning on becoming a lawyer, but changed my mind when I had a really cool science teacher that let us kind of do our own thing and ask our own questions. And so many years later and many degrees later, here I am doing the same kind of research that first sparked my interest in studying science formally. And I really couldn't think of anything better to do than get to spend most of my time outside, playing with different animals, going to different places. I get to travel all the way around the country. I travel around the world with my research a lot of the time. And so it really affords a lot of opportunities, but it affords those opportunities to anyone who's interested. And so it's a really great place to be and a really wonderful thing to get to share, not only with you, but with everyone. So one of the things, I see a Roll Tide there. Roll Tide, yes, that's actually where I got my doctorate, so great places. I'm sorry, I'm trying to follow your questions at the same time. There we go. A lot of questions. Okay, here we go. So did the video play or do I need to play it again? I'm sorry, I just saw somebody note that they didn't see it. So one of the things that I get asked a lot is, did you always know you wanted to be a scientist? The honest answer to that is no. I really didn't figure out what I wanted to be until I had actually gotten into college. I'm kind of non-traditional. And so for a lot of people who think that, oh, to be a scientist, you have to always know you want to be a scientist, you have to go through these elite pathways, you can only go to this school or that school, that's really not true. Being a scientist is more about what's inside of you and your willingness to never give up and your willingness to take every failure, every mistake, every terrible question that you come up with and turn it into something positive. The best advice I can ever give anyone is that failure is where we learn. So I've become a better person, a better scientist, a better researcher, a better mom, all through the failures that I have been through, because it's not about being perfect. It's not about never failing. What it's all about is learning from every one of those experiences and taking it and doing something powerful with it. So my non-traditional approach, I actually started out in a junior college. So I took some classes at the local junior college, which is a really small school. Then I transferred to another small state university and got my undergraduate degree. And as I said, I was planning on going to law school, but I decided that I wanted to work with students as well. So I started doing some volunteer work at that time with an outdoor camp that the university hosted. And because of that experience with the outdoor camp, I decided I really loved science and I wanted to do more working with the public. I wanted to do more on the research side. And so I jumped right in and ended up going to the University of Alabama, Roll Tide again, and pursuing my PhD in evolutionary biology. Now, I spend a lot of time outdoors, but as I told you earlier, one of my major focuses with my research now is actually the intersections of science and society. And that's come about because it's so important for everyone, regardless of where you come from, who your parents are, what part of the country you live in, what religion you are, what your cultural background is. It is so important that everyone have that understanding of science. Not everybody's going to love science. Not everybody's going to have a passion for it. But scientific ways of knowing, the ways we look at the world, the ways we look at evidence in order to solve problems, in order to answer questions, and in order to understand the world around us is a huge part of society, not just as it relates to science, but in all of our decision making. And so one of the things that I like to do especially is talk to people about this intersection of science and religion. So when people ask me what kind of research I do, that's really it. I spend a lot of my time conducting surveys, conducting studies, collecting data, looking at things like evolution. That is a huge part of my research because evolution is something that a lot of people see as controversial. So when you talk to people about that controversy, a lot of times it doesn't have anything to do with the science. It has a lot more to do about things with maybe things that they've heard from family members or friends or beliefs that they have. And so a lot of what I do is trying to understand that so that we can have more conversations about things without people getting uncomfortable. So as far as a majority of my research, I do a lot of that, but then I also do a lot with population genetics. So, somebody's asking me about deer culling. Um, when we look at any kind of organism, so I'm going to talk to deer and fish for just a minute, and then I'll come back to deer culling. But when we look at any kind of organism, one of the things that helps us understand how we get from one species to a lot of species, that explosion of biodiversity, is looking at the genes and trying to understand the events or situations that cause separations in genetics. So one example that I use is looking at fish. There's a really cool fish called a tricolor shiner that's only found in Alabama, and then the other population is actually found in Russia. And we looked at the genetics of this one pond that got split in half by people. They built a military base and split the pond, and we started looking at their genetics and how over time this population and this population, when they're no longer interacting with each other, they start to move in different but slightly parallel paths when it comes to their genetics. So if you think about some of the sci-fi or dystopian movies that you watch, where we have things like factions, you'll notice that the factions, if anybody's a fan of things like Divergent, that there's still intermixing of the factions. So each generation gets to go and select which faction it is that they're going to join. This is an important evolutionary aspect because this is what allows populations to intermingle and allows for greater biodiversity because it increases the genes. Boll weevils, yes. It increases the genes that are available. Whereas when you have areas where there is no intersection, you actually create different situations. We can create them or nature can create them. And we end up with a lot of different things going on at the same time. Why does any of this matter? Because all living things are evolving, including people. And so one of the things that I wanted to show you today is just a very quick video, but I want you to have the opportunity to look at some of the evolutionary changes that are actually visible in your body. So we'll take just a second. And please feel free to check yourself for these different things as it plays.
Your body is a temple, but it's also a museum of natural history. Look closely and you'll see parts that aren't there because you need them, but because your animal ancestors did. No longer serving their previous function, but not costly enough to have disappeared. These remnants of our deep history only make sense within the framework of evolution by natural selection. With your arm on a flat surface, push your thumb against your pinky and tip your hand slightly up. If you see a raised band in the middle of your wrist, you've got a vestigial muscle in your forearm. That tendon you see connects to the palmaris longus, a muscle that around 10 to 15% of people are missing on one or both of their arms. It doesn't make them any weaker though. There's no difference in grip strength. In fact, it's one of the first tendons that surgeons will take out so that they can use it in reconstructive and cosmetic surgeries. You can find the palmaris longus across mammal species, but it's most developed among those that use their forelimbs to move around. In primates, that means the muscle is longer in lemurs and monkeys and shorter in chimps, gorillas, and other apes that don't do a lot of scrambling through trees. It's not the only leftover muscle that we've got. Look at the three that are attached to our outer ear. We can't get much movement out of these muscles, especially compared to some of our mammal relatives who use them to locate the sources of sounds. Presumably, this would have been quite helpful for early nocturnal mammals. In humans, you can still detect the remnants of this adaptation with electrodes. In one study, researchers recorded a spike of activity in the ear muscle cells in response to a sudden sound. Not enough to move the ear, but detectable. And you can probably guess the location of the sound based on these results. It came from a speaker placed to the left of the study subjects. So this is their left ear subconsciously trying and failing to pivot toward the sound. You can see another futile effort by our vestigial body parts when you get goosebumps. When we're cold, tiny muscles attached to our body hairs contract, pulling the hair upright, which causes the surrounding skin to form a bump. for our furry mammal relatives, the raised hair increases the amount of space for insulation, helping them stay warm. Birds can do this too. You've probably seen a puffy pigeon on a cold day. Adrenaline is one of the hormones involved in the body's response to cold temperatures, and it's also part of the fight or flight response. So it helps some animals appear larger when they're threatened. And it may be why surprising and emotional turns in music can give some people goosebumps. And then there's our tail. At the end of our spine are a set of fused vertebrae. Some people have 3, some people have 5. We call it the tailbone. It now serves as an anchor for some pelvic muscles, but it's also what's left of our ancestors' tails. Every one of us actually had a tail at one point. When the basic body plan is being laid out at around 4 weeks of gestation, human embryos closely resemble embryos of other vertebrates, and that includes a tail with 10 to 12 developing vertebrae. In many other animals, it continues to develop into a proper tail, but in humans and other apes, the cells in the tail are programmed to die a few weeks after they appear. Very rarely, though, a mutation allows the ancestral blueprint to prevail, and a human baby will be born with a true vestigial tail. The most adorable vestigial behavior is the palmar grasp reflex, where infants up until they're about 6 months old have this incredible grasp on whatever you put in their hand. There's a similar reflex for their feet. I wanted to show you this great piece of footage from the 1930s.
Agree on something is it's just not something that's going to happen. We tend to be very critical. Not in a negative way, but we're skeptical. So our entire job is to ask questions. Sometimes people get a little uncomfortable because it may be something that to them is controversial. And sometimes people are surprised to find out that evolution is something that is happening in humans even now. I always encourage people to do a little bit of research or take the time to go down to a museum and seek out a Revolutionary War soldier's uniform and just give it a good look. I have a 16-year-old son who is 6'4" and wears a size 14 shoe. If you compare him to the uniforms from grown men who were soldiers in the Revolutionary War, so maybe somebody in their 20s, those uniforms tend to be extremely small. They tend to be extremely short. And that's because at that point in time, the average height for a male was somewhere around 5'6". So to throw a little bit of history in with your evolution, you can imagine that George Washington at 6'3" literally was a giant among men. So we can see this evolution all the time. We see little changes, and evolution is not just a nature thing. Human interaction has caused a lot of evolution to happen even with us. So that's why we get into a lot of these other conversations with things like GMOs, with things like additives in food. What are we doing with medicine and other things that are causing changes not only in the human population, but in other populations as well? I'm sure you've heard about things like antibiotic resistance. So why do I care so much about evolution? It's just a concept, right? Not really. Evolution is important because it's the underpinning theory not only in all of life science, but it's a set of theories and concepts that actually apply across all the sciences. Evolution happens to be one of the areas of science where we have wide agreement, not only across fields, but across disciplines within fields where it literally unifies. We can explain things in terms of deep time. We can explain things with the fossil record. We have genetics and other biochemical evidence. We can even see evolution happening in real time. And so an understanding of this change really helps with our decision making and really kind of gives us this big picture view of life in general, because everything that we do has an impact. And so this ties in really well with biodiversity, not only as the mechanism by which biodiversity happens, but because we really have to be aware that every single thing that we do has consequences. Sometimes those are understood consequences, we anticipate them, but a lot of times they aren't. And so it's a constant process, it's constant learning, and it really gives you foresight and hindsight. I'm getting some really good questions, so I'm going to stop yapping for just a minute and answer. So, what do I like the best about my job? Honestly, I've got an incredibly flexible job. I teach classes at the university, but part of being a university faculty member is also getting to do service, volunteering my time, and interacting with others. So I think the public interaction is one of my favorite things, but it's very hard to choose just one. I spend a lot of time outside. I spend very little time in an office. I get to play in a lab. I get to see all kinds of animals. I get to travel the world. Um, it's hard to pick one thing. It's pretty phenomenal, and I really can't think of anything that I'd rather be doing. I get to spend time with students like all of you. It's really the best job. How long did I go to school and what degree do I have? Okay, so I told you I took a kind of winding path. So I actually started out in junior college taking basics. So my maths, my histories, English, getting those out of the way. And then I went to a state college, and my first undergraduate degree was actually in criminal justice and political science because, as I said, I was looking at being a lawyer. But then when I changed my mind, I added biology to that. So my undergraduate degree also includes biology with that. I then got my master's degree in education so that I could teach while I was going to school. So I have a master's in science education, and I actually have a focus on biology and physics. I have an ed specialist on top of that, which is another year on a master's, and I'll tell you about the years in a minute. And then I have a PhD in science education and evolutionary biology. So I graduated from high school in 1999. I went to school for 4 years for my undergraduate. I went to school for 3 years for my master's, and then I was in school for 4 years for my PhD. So you're looking at somewhere around 12 years. Now, that depends on what kind of program you go into, because now there are a lot of what we call hybrid programs where you get your undergraduate degree, and that's usually 4 or 5 years depending on how you lay out your classes. But then you can go straight into a PhD program where the master's courses are built in. So usually you can get that within 7 years. It just depends on your research. One of the things that you do as a PhD student is you conduct original research and essentially write a book. So it's a very large paper, but you have a lot of time to do it, and you have a committee that provides support and mentorship and helps you through that process. But that usually takes a couple of years after your coursework. So I think a lot of people that I've talked to, it usually takes them between 10 and 15 years total to get all of their degrees done, depending on that pathway. Excuse me. So what biome do I study most? So I'm actually located in temperate deciduous forest, and so that's where I grew up, and that's where a lot of my research takes place. But I've had the opportunity to go to a lot of different biomes. I've been to the tundra. I've been to Africa on the savanna. I'm on a board in South Africa, so I get to travel to South Africa and play a lot. But really, temperate deciduous forests and the coastal lowlands is where I spend a good deal of my time. So that's kind of home base for me. Do I study animals or humans more? Yes, I actually study both. My science and society research focuses on the human condition, and so it really looks at not only science, but it intertwines with culture and a little bit of humanities. So I get to do a lot of philosophy, a lot of history, plus the science and how people feel about science and science policy. But then I also do research with animals. Right now, one of the studies that we're doing is we're looking at how predation, how feeding patterns impact guppies, which are the little fish you can buy at the pet store or get at Walmart. But as it turns out, their color changes very quickly. They have babies very fast, so they're a good animal to study. You don't have to wait very long. But depending on whether they're in an area with a lot of predators or very few predators, their coloration and their size changes very rapidly. In fact, if your classes are interested, if you go to my website, and I'll post that again at the end, we've actually developed guppy kits where you can get the guppies yourself and you can watch that process of them responding to predator-prey interactions. So we've got all those materials for free for your classroom posted online. How long have I been doing this job? Ooh, so I've been in my current job for 2 years, but I've been doing the research for more than a decade because you start your research really as a student and you just build on it and build on it. Prior to becoming university faculty, I actually taught middle and high school science while I was a graduate student. So I've been teaching in some form for about 12 years now. Someone asked, what's the most surprising thing I've ever come across in my research? Ooh, that's a hard question. I guess it depends on what research it is that I'm dealing with. One of the things that I found surprising with the original fish study was that even though our two populations were separated, a lot of the evolutionary changes or genetics changes that were occurring were what we call parallel. So they were evolving very similarly because the environment they were in was pretty much the same. So even though they weren't mixing, we had that co-evolution where they were moving kind of in the same direction. What would be really cool would be to manipulate one side or the other some way and see if that caused changes in those genetic parallels. Average salary for someone in my field. That depends. As university faculty, my salary is 10 months salary, so I can make a certain amount of money that's fixed, and then I can write grants and do other things that add more money to that. The range varies based on the type of university that you are working in. So smaller universities, state universities, and community colleges tend to pay less than large research universities that have a lot of money coming in. But then it also depends on which state you're in. So, you know, a starting faculty member at a university in Louisiana might make $52,000 for their base salary that they can add to. And then, you know, for example, if you're at a research university like the University of Alabama, your starting salary might be $60,000 or $70,000. It's highly variable. It's also very variable based on whether you're in industry, because there are a lot of scientists who don't work as teachers. They work in business. One example of that, if you're interested, a company called Hudson Alpha out of Huntsville, Alabama, actually has businessmen and scientists in this highly technical, state-of-the-art facility working together. And they're doing really cool things with science and business to get medicines and things like that to rural communities, to deliver cancer. In fact, one of their scientists actually developed a molecular glue that helps stick medicine to certain cancer cells. And they were able to partner with business to get that through in 3 years, which is a lot less time than it takes. Usually if you're in a university, it might take 10 to 12 years to get something through because it's a slower process. So, you know, all kinds of cool things you can do. Industry is going to pay higher. As a scientist, you can get a job at the Department of Natural Resources, places like that. It's just very variable. I'm trying to catch up with your questions. What is the peer review process? So peer review is a hugely important part of what we do as scientists. So I always laugh because a lot of people tell me that things like evolution and climate change are just a conspiracy by scientists, that we all got together and we agreed that we were going to mislead people and it's all a hoax. And it's very hard for me not to laugh at that because, quite frankly, I work in a large department. There's maybe 40 people in my department, and getting 4 of us to agree on where to go to lunch is basically an act of Congress. So getting millions of scientists around the world to all agree on something is just, it's just not something that's going to happen. We tend to be very critical, not in a negative way, but we're skeptical. So our entire job is to ask questions. So anything we see, anything we read, anything we observe, we're constantly questioning. Does this make sense? What does the data tell us? What does the literature tell us? Which means, what does other research say? And so with peer review, what happens is you conduct your research, you write a paper on it, essentially, and you submit it to a scientific journal. Scientific journals are very difficult to get into because there's an editorial process as well. So first, the editor reads the paper and decides whether or not it fits with the journal. And then they send that paper out to a panel of experts in the field. So people that have a lot of experience with what you're doing, with the methods that you're using for your research. And basically they take that red pen that your English teacher takes and writes all over your paper. That's what they do. But they're not just looking for things like spelling and grammar. They're looking at, what are the steps that you followed? Are you in line with what the research tells us? Are you doing things the way you're supposed to be doing them? Are you drawing logical conclusions? Are you following the path of the evidence? Because it's not about what we want. It's not about getting the results that we want. We don't set out with a goal in mind. What we do is we set out with a question and then follow wherever that evidence goes. So it's like a really cool scavenger hunt, but all the time. So with peer review, you get all of those reports back from all of those other scientists. And they'll ask you questions and they'll tell you about other literature that you may not be aware of. And really, they give you a very heavy critique of your work. So they'll tell you if they think it's really good, if they think it's not good enough. They'll tell you things that you need to change, things that you need to look at further. And it's ultimately up to this other panel of scientists whether or not your work is worthy of publication. And so anytime a paper comes out in a journal, it's literally been through this process with sometimes 5 to 7 other scientists, sometimes more than that because it can go through a review multiple times, who look at it and determine that you're doing things the way you're supposed to be doing it. That's why when you do research for your classes, they talk to you about primary sources and how important it is to look at the source of information. This ties back to science and society. You have to be able to evaluate what you're reading. You have to look at the news. You have to look at the things that you read in the paper, that you read online, and be a skeptic. You have to ask questions because a lot of times things are skewed. We get a lot of information on one side, we get a lot of information on the other. But most often the actual answer, the truth, lies in the middle somewhere. And so it's up to you to be a scientific thinker, even when you're not doing science, in order to evaluate and make sense of what you're seeing. But peer review is a wonderful part of science because not only does it protect people from misinformation, but it also kind of serves like checks and balances. It keeps scientists honest and keeps people doing things the right way. Ooh, other jobs in biology. Too many to list. You would be surprised at who has biologists actually on staff. Everybody from construction companies to state government, national government, universities, different industries, engineering companies, the military, everybody has scientific jobs. There are so many subspecialties in biology that it would literally take me all day to talk through them. But basically, if there's something that you're interested in, even if it's, okay, I like hedgehogs, there's a field of study in biology for that. So anything at all that you can think of that's alive that you might have an interest in, just look it up. Look up what field in biology studies that, because there really is something there for everyone. So looking at history along with evolution, that's a really good question. So have you noticed any trends with climate change, evolution, adaptation, speed, factors? So one of the big controversies that we hear a lot about in the news today is this argument over whether or not humans are the key factor impacting things like climate change. And so we know that humans have an impact, and we also know that there are a lot of different things that have been going on long before humans really had the technology to alter the world the way that we have. And so a lot of that is still up for debate. But one of the things that we can do is we can look through that historical record. We partner with geologists. We partner with anthropologists. We look at cultures and behaviors and all of these different things that you don't even really think about when it comes to things like evolution, like the importance of things like religion and community in human survival. But we're now starting to realize that all of these things have played a role in how we are evolving, and of course, how we interact with everything around us impacts how they evolve. We've certainly increased artificial selection, everything from domestication to GMOs. It all changes the world around us. But that's the thing. We may change how we do that, but it's going to be very hard for us not to do that because everything is interconnected. Everything interacts with other things. And everything that we do is going to have some kind of consequence down the road, whether it's a positive consequence or a negative consequence. Donna, you said books. Which books, if you don't mind clarifying? Do I believe there is going to be a drastic evolutionary change for humans in the near future? That's an interesting question. As far as the near future, we tend to see evolution happening on a small scale continuously. So evolution tends to be a more long-term thing. It's very funny to me that people who are not really into evolution or have conflicting feelings about it frequently ask me, well, where is the missing link? Well, there was not a magical transition where suddenly an ape turned into a human. You know, that's not really how it works. What really happens is we have very, very tiny changes, very tiny frequency changes in genes. And if you think about it, it makes sense. You know, in every generation, more offspring are born than what can survive. I mean, that's just what happens. Things die, some live. So obviously the ones that live are going to be able to pass their genes on to the next generation. We also see that in all living things there is variation. I mean, look, I've got blonde hair and gray eyes, but look at all the different eye colors, look at all the different hair colors, look at all the different skin tones that are out there. So there's tons and tons and tons of variation in any given population. Now, what if something happened tomorrow, okay? And suddenly the only people who are fit for survival are people that have green eyes, dark skin, and light-colored hair. Well, obviously, if it kills off a large part of the rest of the population, and the people that are more able to survive fit that green eyes, dark skin, light hair profile, then the next generations that are born will very likely have those same traits simply because those traits already existed in the parental generation, and suddenly they're more able to survive than other people. It's not necessarily about being stronger, faster, or any of that. It's just suddenly a trait that's already existed is now more beneficial than other traits. And so that's how we see evolutionary changes taking place. It's really neat to study human evolution right now because the world has gotten so small due to travel. It's so much easier now for people to travel and move and pick up. And so a lot of things that in the past made us evolve differently, for example, skin tone. Depending on what part of the world your ancestors are from, a lot of that impacts the tone of your skin. A lot of that impacts your hair color. A lot of that impacts, you know, frequency of height and things like that. Because it used to be that most people never traveled farther than 50 miles away from where they were born. So there wasn't a whole lot of mixing of cultures or groups. But now that we have a lot of that, we see a lot of changes. We see new traits. We see new combinations. And it's absolutely incredible to get to study these things and have these conversations. A great place to study, and all of their stuff is online, is the Smithsonian Institution's Human Origins program. And you can really look at human evolution not only across time, but starting to look at the anthropological, the cultural, the personal part of human evolution that we're still seeing now. I do have a lot of books that I recommend. Almost Human is a fantastic book. John Hawkes and Lee Berger, who is responsible for Homo naledi, wrote that recently. All of their discoveries in the Rising Star Caves in South Africa are actually available for you to view online. You can actually talk with the team that went down in the Rising Star Caves and brought up a lot of those bones. A lot of really neat stories come from that. Another great one is a book called Darwin's Backyard. It actually has a lot of Charles Darwin's experiments in it, but it also tells a lot of his life story beyond just travels on the Beagle, which is usually what we hear about Darwin. So many books. Anything by Ernst Mayr tends to be fantastic as it relates to evolution. All of those are really, really good books. I can actually post a list on my website of recommended books, so thank you for that. I'll get that up in the next few days, actually, so you can check back and I'll add more. I actually have a library in my house where I have probably 300 or 400 books covering everything you can think of related to evolution, culture that crosses multiple disciplines, so it's kind of hard for me to choose. Community person tells us peer review process is biased. We did learn there are different kinds of journals. How do we find reliable journals? Do you think the peer review process is biased? So anything can be biased because people are involved. People are inherently biased. And so it bothers me when people say, well, scientists are not biased. No, everyone is biased. But what we do is we look at what we call positionality. We really look at our thoughts and our thinking and the ways that our background and our education and things like that impact the way we view things. Now, when it comes to journals, there are predatory journals and there are good scientific journals. And sometimes it can be really hard to determine which ones are which. Some of the top journals in science are things like Nature and Science. And a lot of times if you look at the journal and you look for something called an impact factor means that it's really being read by scientists in the field. If a journal has an impact factor, a lot of times you have to pay to access parts of it. Sometimes you can get PDF versions or you can contact a scientist like me who will share it with you. But those tend to be the ones that have editors that are tied to universities. They seek out people that sit on all different sides of a topic to try to get the most balanced peer review possible. People do say that peer review is biased, that scientists are just going to agree with other scientists, but that's really not true. I can show you some of the reviews that I've gotten, and they literally pick apart every single thing that you say. So it's really a good process. Is it ever without flaws? No, but nothing is. And that's why you have multiple levels of things like peer review and editorial review to kind of ensure that you don't have one person or one entity that controls the voice. So if you go to a journal like Nature or one of my favorite journals, Evolution, Education, and Outreach, you'll see that we have what's called an editorial board. And editorial boards are made up of university faculty and known professionals in a range of fields from all over the country because it gives us different perspective. Because even small things like where you come from impact how you perceive things. So myself as a Southern female scientist, a white woman who grew up in rural Alabama, all of those things are going to impact how I view the world. That's part of my worldview. Just like every interaction with your parents, your peers, your religion, your culture, anything that you do, that's all part of that worldview. And so, being aware of that helps you understand that's the lens you use to judge everything else. And so you have to really work to expand that, to build upon that, and be able to kind of look at the world through a lot of different lenses. And having many people serve on an editorial board like that, and then having this huge cadre, this huge group of possible reviewers, really helps find a balance in all of that. Is there a way to predict genes and traits might be more? So as far as being able to predict what might or might not be beneficial, you could theoretically construct, like a computer program basically and say, okay, well, if this happens, this gene might be more efficient. So, okay, we have a bunch of moles, and one group of moles can burrow deeper than the other moles. So if suddenly the earth got very, very hot, the ones that can burrow deeper might do better than the ones that burrow more shallow. We can make that kind of prediction, but nature has her own mind, and a lot of times the things that we predict don't turn out anything like what we expect to happen. That goes back to what I was telling you about failure. Failure is the best thing in the world because it is really through failure that we learn everything. It's not through success. I have way more failures in my research than I ever do successes, and it's really made me better at what I do. You develop thick skin, and you develop an appreciation and kind of a persistence. You know, okay, this failed, let's do it a different way. Okay, that failed, let's do it a different way. Okay, failed again, what can we do now? So it's just, it's something that we don't really try to predict what's going to happen. We can, we can make those estimates, we can hypothesize, but a lot of times nature kind of throws us for a loop with that. As far as accept and disregard in the world, so one of the things I do study is acceptance and rejection of evolution among the public. And I do a lot of that research in the South, but I do it nationally, and I have a lot of peers that I collaborate with around the world. And in the United States, we have a pretty low rate of acceptance of evolution, which means, not really whether or not you know about it, but whether or not you think it's really a thing. Um, and so in other countries around the world, in other cultures around the world, we don't see as much of that. We don't see as much of the conflict. And a lot of that has to do with, again, history, religious freedom in the United States, a lot of different cultures that are represented and things like that. And so here, at least, acceptance of evolution is a very big problem. I want to say most recent data from the national polls is that only about 19% of the population accepts evolution, including human evolution, that basically all living things on Earth are evolving. And so that's a pretty low number considering as how evolution is seen by scientists as the unifying theory, not only in life science, but across all the sciences. That's one of the reasons I do what I do, because I want to be able to bring people to the table. I grew up Southern Baptist in a literalist creationist family. A lot of my family is in the ministry. And so evolution was something that conflicted strongly with what I was being taught at home and at church. But the more I learned about it, because luckily, my grandmother taught me to read a lot and encouraged me to read and find answers for myself and not just take everything that I saw or heard as fact. And so the more I read, the more I thought, this makes sense. The science makes sense. And then, it was up to me to navigate how that fit in with the beliefs that I grew up with. And I think a lot of times we don't afford people that opportunity. A lot of people think that you're either scientific or you're religious, and that the two are in controversy or in conflict with each other, and that's really not the truth. You can be religious, you can be very devout in your faith and still be a very good scientist and still be scientifically minded. And so what I do is try to bring people past that conflict, past that controversy, so that we can have conversations about that by saying, hey, look, science doesn't seek to prove or disprove the existence of God. Science is a physical explanation of events in the physical world. We can't consider supernatural responses. We can't consider the metaphysical because they're not testable. It doesn't mean that science is better than beliefs. It doesn't mean that science is better than philosophy. They're just all different ways of viewing the world, and it's important that we all have understanding of multiple ways of viewing the world. To me, that's what's going to solve a lot of our problems, not just in science, but in society, because we have to be willing to listen to other people. We have to be able to empathize with where people are coming from and the experiences that other people have so that we can better understand each other and grow and do better things. Being more open-minded and understanding and being able to just sit down and have conversations even if the person we're talking with sees the world very differently than we do. Any other questions? I'm hoping you can tell how passionate I am about my research. It's something that's very important to me. I really feel like there are a lot of people that are on one side of the aisle or the other, and this applies to science, this applies to politics, this applies to gender issues, this applies to racial issues, this applies to ethnicity issues. It applies to so much more than science, and that's one of the reasons I put so much into what I do, because that middle ground for all of us is hugely important. Science, and specifically evolution, to me simply represents one venue to get those bigger conversations started. Regardless of what you believe, regardless of where you come from, regardless of your education, your family's education, your immigration status, your gender, your race, your ethnicity, whatever it may be, it's important that everyone have the ability to understand science, to think scientifically. It's important that regardless of what worldview, what lens you use to look at the world, that you can also have a scientific worldview, that you have multiple ways of understanding and viewing and looking at the world around you. And please feel free to ask questions. Yes, climate shifts with global warming. Snow in Georgia, yes. So just a quick kind of funny story. I've lived in Georgia for 2 years. My best friend who grew up here said, "Oh no, come to South Georgia. It's always warm. We haven't had a hurricane in 50 years." And I've been here 2 years, and I've made it through 2 major hurricanes and a 3.5-inch snowstorm in coastal Savannah. So I'm starting to think it's me that's the problem. I could be wrong on that. As far as climate change, one of the things that we have to realize is that even if you take the human element completely out, which when people argue about climate change, that's really the only point they're arguing about, whether or not human activity is the cause of climate change, because back and forth throughout time, and we can track this back for hundreds of millions of years and further with things like ice cores and samples and things like that in geology, where we can literally have this very cool historical record of what climate was there, of rainfall, of chemicals in the air, of what kind of things lived and survived and thrived. And so we know these things are happening. Climate change is happening. Warming and cooling happens. We go through ice ages, we go through hot periods. We'll go back to an ice age and back to a hot period. The thing is, we need to know whether or not humans, that industrial impact, our technology over the last few hundred years, is one of the major factors, and that issue alone is where the argument lies. It's not whether or not climate change is real, because it is. Climate change and global warming are real. They are happening. The only argument that exists is whether or not people believe that it's being exacerbated, being made worse by human activity, or whether it's just happening anyway. And that's a very detailed and very long conversation. But climate change, regardless of your stance on whether or not humans are the cause, is absolutely real. And we're going to see more extreme weather. We're going to see a lot of things changing. We're going to see a lot of warmer weather. We're going to see a lot of weird cold weather, because global warming isn't just about things being hot. It's about changing climate patterns over the long term. It's not just about weather. It's about long-term shifts in everything from the temperature of the Gulf Stream to the coastal prevailing winds to the Santa Anas, everything around the country getting changed by those changes in radiation and other things in our environment. How do I feel the future of education and evolution will change in the next few years or decade? It is my sincere hope that, as we continue to study and understand these things, that we're going to change the way we approach conversations with the public and with students about evolution. One of the projects that I'm a part of with the Smithsonian Institution, as well as another project I'm a part of with National Geographic, we're looking at developing materials and helping teachers develop more approaches that are not based on lecture. And that's the big thing. That's one of our biggest issues with evolution education, is that for the longest we've looked at things as, oh, you don't accept it, so obviously you're ignorant and I need to just tell you more about it. That may be true with a lot of topics. For example, the more you know about photosynthesis, you can observe it, you can manipulate it in a lab, so you become accepting of photosynthesis. But with things like, but maybe they're learning about, and so they actively reject it even though they know a lot about it. Learning about, and so they actively reject it even though they know a lot about it. Just like some people are all about evolution, but if you ask them questions about the content, they really don't know a whole lot about it. So we have to really change our approach, and that's where that listening and learning and finding new ways had the chance to evolve again. Do you feel this view has merit? I will say I don't feel that view has merit, and this is why. We're evolving. Had the chance to evolve again. Do you feel this view has merit? I will say I don't feel that view has merit, and this is why. We're evolving now. Evolution never stops. It's not possible. It is continuous and ongoing in all living things. And so as far as humans, excuse me, humans going the route, of time machine, where you have two separate groups of humans, who knows? Who knows when, something like that may or may not happen. And yes, it is possible that we could all wipe ourselves out. But as far as before we evolve again, that language, we're evolving even now. We're constantly changing. If you think back to the video that I showed you, touch your fingers together, your thumb and your pinky together, and bend your hand up. You can see that I do not have a palmar longaris. I do not have that tendon in my hand. But a lot of people still do. We have people that are being born without appendixes. We have people that are being born without, and never develop wisdom teeth, because these are just small frequency changes that are continually happening. And so we're constantly evolving. I think I'm about out of time. So what I'm going to do is I'm actually going to put my slide back up. If you have any questions, if your class has any questions, if you would like to talk to me, please feel free to send me an email or to catch me on Twitter or to go to my website. There's a contact form there as well, and I will make sure to answer you. So that's EvoPhD on Twitter if you tweet. AmandaLGlaze.com is my website, and then my email is aglaze@Georgia Southern University. Thank all of you for joining in with me today and for asking really good questions and for listening to me talk about what I do. I love what I do, and it's absolutely wonderful to have opportunities like this to share with others.